Howard policy iteration, or sometimes just policy iteration. And then another algorithm called optimistic policy iteration, which is kind of like a convex combination between these two methods. So we'll discuss these methods in the context of a fairly simple problem. And along the way, we'll discuss how these algorithms might interact with function approximation architectures or neural networks or machine learning once we start adding that stuff on top. The problem, like I said, it's a really simple problem, but I wanted to make it at least a little bit interesting. So the little bit interesting is going to be that the discounting is not constant. It's going to be time varying. So we'll just throw that in to make the problem a little bit less boring. We'll solve it using these three different algorithms, and then we'll look at some code to actually implement the algorithms. And that code is going to be in Julia and a couple of different flavors of Python. We'll look at how fast they run, what they like to code in, and kind of compare them and discuss which ones are useful in which situations. So that's the basic one. Okay, so this model that I'm looking at in the whole discussion is based on what's coming out of chapter 6 of a book that I recently completed. Touch wood that it's completed because I keep finding typos and then going back. But it's getting pretty close, I think. If you do find typos, if you do read it, and you find any typos, I would, of course, love to hear about them, preferably before November 15, which is when I have to hand it over to Cambridge University Press. Yeah, but I think it's pretty good now. I think it's in pretty good shape. So anything that I talk about where I don't give full proofs or you'd like to know a little bit more details, please have a look at that chapter. Okay, there's a link to the URL there, and there's a free PDF. Okay, so the problem looks like this. So I'll start off with a super simple version and then complicate it a little bit. It's a problem of inventory management. And the Bellman equation looks like what you see here. So Y is going to be current inventory. And A you can think of as your action, and in this case the action is how much stock you're buying in the current period. So as a function of your inventory levels and how much stock you buy, we're going to get some amount of profits. Where's my little shiny thing? Why doesn't my shiny thing work? Because I'm pointing it the wrong way? I use the mouse. I'll go old school. This one. Just not strong. Okay. All right. So yeah, this is current profits, which depends on the state and the action. Beta is the discount factor, and then V is like a value function. And this guy here is going to be the transition probabilities for inventory. So Y is inventory today. We order a certain amount of inventory, that's A. And then we arrive at inventory Y prime according to this probability embedded in R. That's like transition probabilities across all the Ys, and it's going to be stochastic because there's stochastic demand. It's going to determine the level of inventory we have next period. So there's some details about the particular functions that I've chosen for profits and so on, which we'll see once we get to the code, but that's the basic structure. And as you can see, it's a very generic looking Bellman equation. When we do get to the code, you'll notice that one feature that I've built into the model is that current profits are going to be affected by a fixed cost of ordering. And because there's this fixed cost of ordering, we're not going to be ordering small amounts all the time. We're going to wait till the inventory appreciates with demand. So people are buying stuff, inventory is going down, and then we order a substantial amount, and go down and order, and go down. See the dynamics look something like. Okay, so this is a very simple model. It's probably unrealistic in many different ways, depending on the application. One way that it's unrealistic is that discounting is constant. So in a model like this one, where we're maximizing the present value of a firm, you might expect that the discount factor is 1/1 plus the interest rate. And the interest rate, as we know, is typically time varying. So whether we look at nominal interest rates or whether we look at real interest rates, you're going to be moving around over time. So in practice, this discount factor is not going to be stationary, it's going to be shifting around. So how would we incorporate that in the model? So that's the little twist that we'll add in to this dynamic program. One thing you'll notice is that, at least if we look at real interest rates, and sometimes with nominal, we see negative interest rates. And if the interest rate is going to be negative, this beta is actually going to be greater than 1. So ideally, we'd like to look for conditions that allow beta to drift above 1, which it's kind of like a little bit tricky because, as you can imagine, if we think about this beta in the traditional theory of dynamic programming, that makes it a contraction mapping because it's less than 1. Right? Here we're going to allow it to drift around a fair bit. Okay, so with state-dependent discounting, if I think of a time t reward, let's call it RT, and I'm discounting it from the present, and I've got a discount factor that's moving around over time, the current value is going to look something like this. It's the expectation of this product of the time-varying discount rates times the reward function. So what I want to do is, first, let's think about how to compute lifetime values when the discount rate is moving around. And then once we've figured out how to do that, let's think about how to optimize it. We'll bring in a theory of dynamic programming, then we discuss the algorithms, and then we'll implement the algorithm. That's it. So I'm going to start with step 1, which is computation of lifetime values in a scenario where we're discounting like this across these products. Okay, so the way I'll do it, let's take a state process. It's just some stochastic process which is going to be driving uncertainty in the model. And I'm going to assume that it's a Markov chain. It's going to affect the discount factor, and it's also going to affect things like profits, revenue. So what I'll do is I'll introduce a Markov matrix on the state space. So CapEx is the state space. And then this Markov matrix, or kind of like a transition function, if you like. This is just the probability of going from x to x prime in one step, one period of time. And then this guy, I'll say this is P Markov on CapEx. So what I mean by that is it's just a Markov chain that's driven by these transition probabilities. And I'm keeping everything finite just to make our life simple. Okay, so we've got a Markov chain. This Markov chain is going to be affecting the discount rate or the discount factors. So in particular, when I discount at time t, my time t discount factor is this product here, which is affected by the X process. So that product that you're looking at there is this guy. So it's just a situation where these betas are driven by the state process X. So that's our time t discount factor. If, for example, this B was going to be equal to a constant beta, then obviously this product would be just beta to the power of t, and we're back to the traditional model. Okay, so to handle this kind of discounting, what I'm going to do is I'm going to introduce what I'll call a discount operator. It's really just a matrix, which is this guy A. So AX, X prime is going to be the product of B. So B is this one period discount factor times the transition probabilities. And I'll let rho of A be the spectral radius of A, which is the maximum in modulus of all of the eigenvalues of A. Okay, so what we're interested in is computing lifetime values or infinite sums. And the infinite sums are going to look something like this. So we've got delta being the discount factor, which is the product of these betas. We've got some kind of time t payoff, which is h of xt, so that's also driven by the state process. And I'm taking the expectation over the infinite sum, and that little subscript small x here is just indicating that the initial state is little x. That's where the state process is starting off. Conditional on starting there, I want to evaluate this expression. And in fact, it's not hard to show that if the spectral radius of A, which is our discount operator, is strictly less than 1, then this guy is going to be finite at every little x. And moreover, we can compute it as this geometric sum. Or we can compute it via this inverse method. These two things will be equal, under the condition that the spectral radius of A is less than 1. So incidentally, if I take, let's say this B here is equal to a constant beta. Does anyone know what the spectral radius of this guy is going to be? Spectral radius is A. Yeah, so what would the spectral radius of A be? So let me ask the question differently. What's the spectral radius of P?
1.
Yeah, that's right. So the maximum eigenvalue is going to be 1. And this would be a constant. If that was a constant, we could just pull it out, right? And then the spectral radius would just be beta, which is less than 1, we assume. So everything's going to work. So this condition on the spectral radius is like a generalization of that. Generalization of beta less. But it's actually going to allow this process to be pretty flexible and sometimes drift above 1, sometimes below 1. Should still be fine. Okay, so can I get rid of the layer?
Yeah, can you speak?
Yeah. So how does this work? The reason I'm spending a little bit of time on this is that we want to maximize lifetime values. But if we don't know how to compute lifetime values, we can't maximize them. So at this stage, we just want to learn how to compute these lifetime values, and we'll go on to maximize them. This is a sketch of a proof of the theorem on the last slide. And the only thing that's remotely tricky is this equality here, which is just saying that if I look at the expectation discounted, the expected discounted value, remember h of xt is something like a payoff. So I'm computing this payoff, discounted present value over these time-varying discount factors is just t applications of the discount operator. And if you want to convince yourself of that, you can start off with t equals 1. You write down both sides of that expression, and they're exactly the same thing. And then you just do induction. So hopefully you'll allow me to just work with this, go on from this step. And once we take that as given, then I'm going to start here, right? And I take this expectation, I pass it through the sum, which is all safe here because we're working with a finite state space. And then I apply this equality here. I get this expression, which just says that V is equal to this geometric sum. And then by one of the most valuable results in all of applied mathematics, the Neumann series lemma, sometimes called geometric series lemma, I know that if the spectral radius of this guy is less than 1, then this geometric series is going to be equal to this guy here. And if by some chance you've never seen this before, think of that as just a number, a scalar. And then surely this is true, right? We learned that in grade 10 or something. And that extends to matrices and also extends into infinite dimensional space as well. Okay, so that's why we have B equal to this geometric sum is equal to this inverse expression. So we'll actually use this when we want to compute lifetime values. We're going to be using expressions like this. Okay, this condition is weak. I already kind of said that, so let's skip over it. Okay, so we now have some idea of how to compute lifetime values. Let's look at dynamic programming in the presence of time-varying discount rates, like state-dependent discounting. And rather than looking at it directly for this inventory model, I'll give you a slightly more general result, and then the inventory model is going to be a special case. So the model we're going to look at is a Markov decision process with a Bellman equation that looks like this here. So this is like the value function. X is the state, A is an action, gamma of X. So this is feasible correspondence. It's telling us what we can do at this particular state. I'm summing over next period states. So the only interesting, the P is transition probabilities for the state. So given the state and the action, this is the probability I end up at X prime tomorrow. And the only interesting feature here is that the discount factor is allowed to be time varying. It's state dependent, depends in general on the current state, the next period state, and the action. Okay, so a feasible policy. When we maximize, we're going to look at the best feasible policy. So policy is just a map from states to actions. So this symbol here just means all the maps from states to actions. There's a map from states to actions that's everywhere feasible. That'll be a feasible policy, and then cap sigma is going to be the set of all feasible policies. So once we pick a feasible policy, that tells us what our action is going to be in every state. Once we know what our action is in every state, that pins down our rewards as a function of the state, our transition probabilities as a function of the state, and our discount factor as a function of the state. So intuitively, when we pick a particular feasible policy, the Markov chain that's now driving the state is going to be this P sub sigma. That's going to generate a state process. And then we'll get rewards off it determined by these other couple of primitives. So for a particular feasible policy, the lifetime value of that policy is going to look like this expression here. So expected sum of discounted rewards, payoffs, and the discount factor is depending on beta and on the underlying state process, and the state process is depending on the underlying Markov process, and that's depending on the policy. Unfortunately, now we've done a little bit of investment in computing lifetime values when the discount factor is changing. I know when this is going to be finite and I know how to compute it. I just take the discount operator. This is what we called A before. It's just the discount factor multiplied by the transition probabilities. I take that guy, I check the spectral radius is less than 1. And if it is, then lifetime value of the policy is given by either this geometric sum or this expression here. This is a typo. This should be R sub sigma. My bad. Okay, so this guy here is the one that we'll typically be using in practice when we want to compute lifetime values. The only potential issue with using this to compute lifetime values is that this guy could be very large. So if the state space has n elements, this is going to be n by n. So if the state space has 1,000,000 elements, it's going to be 1,000,000 by 1,000,000. And that's potentially problematic. So we'll discuss methods for handling that situation as well. Even though the state space we'll actually look at is pretty small. Okay, so yeah, so because we're concerned with computing lifetime values, we'll talk also about what's called a policy operator. So the policy operator is a little bit like the Bellman operator, but it's at a fixed policy. So instead of choosing the optimal action, you're just going to stick to a given policy and follow that. So in this instance, the policy operator looks like this. R sigma plus L sub sigma on V. And you'll notice that V sub sigma, which is our lifetime value of the policy sigma, to say that V is equal to this guy is to say that V sub sigma solves this equation, which is the same thing as saying that V sub sigma solves this equation, which is the same thing as saying that it's a fixed point of the policy operator. Any questions so far?
You said there was a typo on the slide before. It was supposed to be an R.
R sub sigma. This one.
So it's not an L, it's an R.
No, L is right. L is good, and V should be R sub sigma.
Oh, V should be R sub sigma.
Any other questions? Okay, so I've got it right here. Yeah, okay, so we have a few different ways to compute lifetime values now. In fact, what we can do is we can take the policy operator and iterate with it. So we know that lifetime values are fixed points of the policy operator. It's also true that under our conditions, the policy operator is going to be globally stable. So wherever we start off, we're going to converge to its unique fixed point, which is the lifetime value of the policy. So that's going to matter for us once we get to implementing our algorithms. Yeah, so now we have a few different ways to compute lifetime value. If I fix a policy, I can compute lifetime value using this geometric sum. I can compute it like this, using the inverse method. Or I can use the fact that the policy operator is globally stable. I can pick an initial V and start iterating with this guy, and I'll converge to V sub sigma, the lifetime value. All right, so then the question is, what's more efficient? And it kind of depends what we want to do and what the size of the problem is like. As we were saying before, this could be problematic if it's a very large state space. And also sometimes we don't necessarily want to compute things exactly. I'll say a bit more about what I mean in just a second. All right, so then we can state a theorem about dynamic programming in the presence of a discount factor that depends on the state. Yeah.
interpretation of this V0 here, because say the policy maps from any particular state, right, to an action. And are we ensured that we will, like, explore the full state space given policies? What exactly is?
We're yet to optimize over policies. Yeah, so that actually comes next. At this point, all we've done is fix the policy, and we want to know how much value it gives us.
Yeah, but see, I drop the agents in place in state space. It's not. We're not guaranteed by the policy that we would end up there by some other place in state space, right? So it might only, the value of a policy might only represent the value of a small subset of possible states, right?
Yeah, this is going to compute the value of the policy globally at every x. So this V sub sigma is a function on the state space, and it's going to give us the value at every single point in the state space. Now, whether we actually want to do that or not is a different question. In some algorithms, we might not want to do that, but this is going to give us the full thing.
But is there then some sort of restriction on the policy that we will, with certain probability, enter each state? There must be, right?
No, I wouldn't think so. I mean, at this stage, we're just looking at all feasible policies, and we want to compute the value of any given feasible policy. Now, which is a good policy? That's a different question, and we'll get to that in just a second.
Yeah, I don't think that's what I'm getting at, but maybe we can see it.
Yeah, for sure. And as I go along a little bit more, it'll be a bit clearer. But yeah, I'll try and answer your question as best I can. Okay, so this is kind of, yeah, maybe I'm gonna skip these details. So essentially what we know is that, like, as long as this L sub sigma guy, what we've learned so far is, as long as this L sub sigma guy has a spectral radius less than 1, so it's like our discount operator, has a spectral radius less than 1, the lifetime value is going to be finite, and we can compute it. Now, we'd like a condition that says that's always going to be true across all of the policies. And to do dynamic programming, we sort of have to impose that. So when we look at the actual theorem that I'll show you, it's saying a little bit more. It says, like, there's some dominating guy L, which is bigger than all the L sub sigmas, and that guy has spectral radius less than 1. But I think let's skip these technical details so we can get onto the implementation. Okay, so we've got this. We need a condition under which lifetime values are finite and we can compute them. Otherwise, we're going nowhere. So we've got this condition, and the condition that we're going to impose looks something like this, but let's not worry too much about these details. Let's move on to defining optimality. So once we've got lifetime value at every possible policy, then the value function, we take all of the policies over the set of feasible policies and we maximize. And that's the definition of the value function, which I'll call V star. And then a policy sigma is going to be optimal if it attains this. And remember, these are functions. So this is saying that at every state, this policy is going to give me the maximum amount of it. Standard definition of an optimal policy. In our setting, the Bellman operator takes the form you see at the top of the slide. No surprises there. Bellman operator I'll call cap T. And this is a bit of notation that I use that's useful when we describe the algorithms, which you might not be familiar with. So I'll call a policy V greedy if it's the case that it's in this argmax for every x. And what that means is, think of this guy as a guess of the value function. We take that as our guess of the value function, and then we maximize with respect to the action to figure out what we should do. So the basic results from dynamic programming tell us that if this guy is the value function, and we take the greedy policy with respect to the value function, we get an optimal policy. So that's all greedy means here. Anyway, this is the definition of V greedy, which we'll use a little bit as we go along. Is that clear?
It's just the arguments, right?
Just the arguments, nothing else. Just a little piece of notation that I.
But it's not greedy in the sense of maximizing current return. It's like greedy in the sense of a lifetime.
It's greedy with respect to V. Yeah, that's right. Okay, so now we have a result. And this is like a general result for handling state-dependent discounting. And it says if there's some dominating guy L, which is basically bigger than all of the discount operators that we could face. I'll show you how to check this condition. Anyway, we need some condition like this to make sure lifetime values are finite. If that's the case, then the policy operators are all going to be globally stable. And their unique fixed point is going to be the lifetime value of that particular policy. The lifetime value of any given policy looks like this. Bellman operator is globally stable. A policy is optimal if and only if it's V star greedy. So that's what we just said. And at least one optimal policy exists. So this is telling us that all the basic results of dynamic programming go through. And it's also giving us a little bit more information about how we might want to compute lifetime values. And that's going to be useful for us when we look at different algorithms. Okay, so let's move on to algorithms. The algorithms we'll look at is value function iteration, powered policy iteration, optimistic policy iteration, as we said before. And we'll try coding them up and seeing how they perform. So value function iteration is what we all learn when we first start doing dynamic programming. It's straightforward. I take a guess of the value function, and then I just iterate with the Bellman operators. Just doing successive approximation with the Bellman operator, which in this case is globally stable. So we're going to converge to V star value function. Everything is going to work nicely.
Can I ask something for
Yeah.
this algorithm? So like typically we adjusted in the policy, right? The value function is nothing. So like, can you just comment a bit with the audience, what you consider good, like the line layer abstraction, so like again compute the remaining policy, but like you would also probably compute the difference between.
How close is the policy that you end up with to the true optimal policy? Yeah, it's a good question. So you can come up with bounds, error bounds, and they'll be determined by the primitives of the model, plus how many times you iterate, or your error tolerance, but they tend to be very pessimistic. So we can come up with bounds that'll say that the performance is going to be better than this, but usually the performance in practice is going to be much better than the error bounds. So I'm not really aware of any theory that's giving us really tight error bounds across a range of different situations.
But then like, practical question then, so like, at which level do you stop in your growth? Epsilon is -6, or what does it imply for the growth?
Yes, yeah, so what does it imply? It's hard to say. It's hard to say. Again, we have theory, the theory is not super useful. It's not, those bounds are really pessimistic. They're just not tight. In practice, when we look at the code, look at e to the -6, and in fact, that's going to terminate at the exact optimal policy for this small.
Yes, it depends on what you want to use it for. If you want to use it like solve a dynamic programming within an estimation routine, trying to solve for an equilibrium, and you need to calculate numerical derivatives and so on, then you don't want to have like small tolerance, too big tolerances, because then you change parameter a little bit, and then you end up with the same solution, and the derivative is 0, and it kind of goes down.
Yeah.
Other situations, you just want to look at the solution, maybe you can be more loose.
Yeah, yeah. Yeah, it's sort of horses for courses. Okay, so this one's pretty straightforward. The next one is Howard policy iteration. So Howard policy iteration, if you haven't seen it before, what we're going to do is we're going to input sigma, which is a policy. And then I'm going to take that policy and I'm going to compute the lifetime value of that policy. Once I get the lifetime value of that policy, which is a function of v, I'm going to take that v and get the greedy policy. And I take that greedy policy, I get its lifetime value. Take the lifetime value, I get the greedy policy. So the iteration looks like this. I start with some policy, I get its lifetime value. I take the greedy policy, lifetime value, and so on and so on. How many people have coded up Howard policy iteration? Okay. So about a third of people.
Find the greedy policy.
How do you find the greedy policies?
How do you find that sigma k plus 1?
That's actually pretty straightforward. So the greedy policy is just coming from this line here. That's actually your easy step. Once I've got my V, I'm going to get this guy as the greedy policy. So that's cheap.
Require a maximization routine? Or?
Yeah, that's right. Yeah, and that's, you know, the difficulty of that varies with the problem.
Are we assuming that there's like a finite number of policies or feasible policies?
In this case, I'm assuming that there's a finite number of states and actions. So computing this guy is not going to be an issue.
Okay.
But in general, computing this guy is pretty cheap. The step that's expensive is the other one, which is finding the lifetime value.
So because that's like a big matrix.
Yeah,
Get under it.
yeah, exactly.
So could you go back to the stopping criteria? So when we're using the infinity norm and the VFM, we could be spinning our wheels, optimizing states that are off the equilibrium path, right, or far from the equilibrium. Do we see like empirical gains from focusing on path?
Yeah, so I guess so. So you're talking about some kind of Monte Carlo routine?
Or just like, you know, if there's an area of the species that we're very rarely going to visit, it's giving us a high infinity deviation. We might just not care about that.
Yeah, for sure. Yeah, so that's right. I mean, there's a bunch of different tricks. I mean, I don't think the infinity norm is really the issue. Particularly in this setting, like all of the norms are going to be essentially equivalent because it's finite dimensional. But yeah, so there's potentially lots of tricks that we could use to speed up value function iteration that way.
You know that once sigma k equals sigma k plus 1, this thing terminates.
Yeah, it's a good question. Yeah, so if you look at the stopping criterion here, I'm not using any norm at all. I'm going to stop once we get exact equivalence of the two policies.
Is there like a mathematical proof that that means that you found the optimal policy?
Yes, absolutely there is, yeah. So in fact, when there's finite states and actions, Howard policy iteration is always going to converge in a finite number of steps. And the thing that it returns is the exact optimal policy. That's kind of like a neat thing about it. So you may have seen already that Howard policy iteration is something like Newton iteration when we're trying to compute the fixed point of the Bellman operator. So this is a one-dimensional picture of what's happening. The one-dimensional is obviously like super simplistic, right? We imagine that we've got one state. People got really angry when I showed this slide in the last talk I gave. It felt like this is ludicrous. Okay, but I find it useful to really abstract this and try and get a feeling for what's going on. So don't get angry. Hopefully it's useful to you to think about it in this way. So what you're looking at here, so the blue line is going to be the Bellman operator. Then the orange line is a policy operator. And if you think of what the Bellman operator is, you're taking a max over all the policies And that means you're actually taking the upper envelope of all of the policy operators. Now, if I take a particular V and take the greedy policy, that's where T sigma is going to be equal to T. So T sigma, because I'm taking a greedy policy, I'm maximizing, I'm doing the same thing as the Bellman operator. So that's where these functions are agreeing. So I take a greedy policy, and then I take the lifetime value of the greedy policy, which is the fixed point of the policy operator. Then I take a greedy policy. Again, I'll take the tangent line. So you can see what we're doing here is exactly Newton policy, Newton iteration. Newton iteration on the Bellman operator. The value function iteration is simple fixed point iteration with the Bellman operator, and then how it is Newton iteration.
How do VFI look at this picture?
VFI? Yeah, so VFI, we take the blue line, right, and we're just doing ordinary successive approximation. So we just fixed point iterating on this guy. That's value function iteration. Howard policy iteration, it jumps to the lifetime value. I go up here and get the tangent line. Once I've got the tangent line, I follow that to the fixed point associated with that tangent line, and you can see that we're going to be almost there already. So the difference, the essential difference is Howard policy iteration, variation on Newton's method. It's going to be a smaller number of more computationally expensive steps. And that's potentially advantageous when we start thinking about parallelization and putting things on GPUs. Because if you think about something that's very sequential, it's hard to parallelize. Whereas if we have something that's less sequential, more of the work is done in a smaller number of computationally intensive steps that we can potentially parallelize, then there's more we can accelerate when we take it to a parallel algorithm or onto the GPU. Okay, the other algorithm that we look at is optimistic policy iteration. Who's implemented, oh, maybe I'll tell you what it is. Okay, so optimistic policy iteration, I think I described it as a convex combination of value function iteration and Howard policy iteration. That's roughly what it is. So think of Howard policy iteration. So I've got a VK, I take the greedy policy. Now, after I take the greedy policy, I'd compute its lifetime value. Here, I'm not going to do that exactly. So what I do instead is I take the policy operator associated with the greedy policy, and I start iterating with it. So I've iterated with it m times, and m is like a parameter in the algorithm. If I take m to infinity, I know that this guy is going to converge to the lifetime value of that policy. So m equals infinity is Howard policy iteration. Now, if I set m equal to 1, I'm actually just doing value function iteration. If I set m equal to 1 and I take a greedy policy and I put it in here, I'm just applying the Bellman operator, nothing else. But now we have a parameter m that we can adjust and go between these two extremes, potentially do better.
Why is it not, if m is infinity, you iterate it an infinite number of times, is that what value function iteration is, or?
No, because, yeah, good question, but no, because it's the policy operator that you're iterating. Yeah, rather than t. So this, yeah, so I'm gonna, it's a good question. I get this greedy policy, I'm gonna freeze it. Right? And now I take the associated policy operator, and I start iterating with that guy, but I'm not maximizing anymore. I'm just iterating with the policy operator, which is kind of cheap because it doesn't involve a max step. I do that m times, and I get an approximation of the fixed point. So if we go back to the picture, I'm iterating with this orange map. So I'm going to bounce to here, and to here, and to here, and to here, over m steps. And if I take m all the way out to infinity, I'm actually going to get there. And that's how it. Any questions, comments? Everyone's happy? All right, so there's a proof in the book in chapter 6 that shows that all of these algorithms converge under the stated condition. And how a policy iteration is going to converge to an exact optimal policy in a finite number of steps. Okay, so there's no questions about algorithms? Yeah.
Why is it BFI if you set m equal to 1?
Okay, so if I take a VK greedy policy, I'm actually maximizing with respect to this guy. When I maximize with respect to this guy across the actions, that's nothing but the Bellman operator. I apply that once, and then I go back to here. So there's kind of like an extra step in it, but it's actually equivalent. Yeah, because you're maximizing with respect to this specific function. So that means that you're choosing the best actions given that guess of the value function, which is the same as applying the Bellman operator.
So why not use HPI all the time? Is it just depends upon the computational cost of that step in the policy HPI?
Yeah, good question. I mean, so my guess is that people use HPI less than BFI because it's a little bit harder to code.
But why OPI, I guess, that is somewhat,
Sorry?
why the optimistic policy iteration?
Or why would you have that? Why instead of, yeah, good question. It typically turns out to be faster for some choices of M. And I guess the answer is that it depends on the problem. And the one we'll look at, it's actually a little bit slower in most cases than Howard. I mean, I guess intuitively, like, you know, doing Howard, you go exactly to here. And then you do the next step and exactly to there. But maybe that's really expensive to exactly evaluate the lifetime value.
Yeah, so you're not inverting the
Yeah, so yeah, maybe it would be cheaper to use a simple iterative solution rather than like some hardcore.
That's a language state.
Depends on the size of the state, yeah. Now, yeah, there's actually, so if the state's really big, then Howard becomes problematic. But when we look at the code, I'll show you a way around that, which is maybe like a blend of Howard and an optimistic policy iteration anyway. Yeah.
Wouldn't it be the case that you need to use value function iteration if you have breaks in the policy function in the value function?
Breaks in the value function like discontinuity or something like that?
Yeah.
No, that's not the case. So this.
But then how do you calculate the tangent line?
Yeah.
I suppose that
Yeah, so let me be careful. I mean, at present, what we're talking about is finite state and action spaces. In that case, we're guaranteed that it's going to convert in finitely many steps. Now, would Howard be difficult in a context where you've got jumps in the value function? Sure. So you think you would make it harder to compute lifetime values?
yes, because you're dependent on the tangent line, and if you cannot calculate it in breakpoints.
I have to think about that. It's a good question. I'll think about it.
The proofs that VFI, HPI, and OPI all converge, don't you get that once you know that the Bellman operator is a contraction? I mean, you're using this model that deviates from Blackwell's conditions, but you kind of flexed and showed us that you proved the existence and uniqueness of that Bellman operator. And once you have that, shouldn't VFI, HPI, OPI, when you kind of get that, or it's the same proof?
Okay, so I didn't mean to be flexing so more generally. Yeah, so that's right. So in this situation, the Bellman operator is not a contraction mapping. So yeah, but it's like an eventual contraction. Convergence of the Howard policy iteration routine you can prove in situations where there's no contraction at all. But again, I'm talking about finite state and action spaces. Yeah, but the general method extends to very, very abstract kind of problems. And in fact, the talk that I'll give at the end of the summer school is going to discuss settings like recursive preferences, Epstein-Zinn preferences, risk-sensitive preferences, so on and so forth. In these situations too, you can prove that it converges. So the convergence is super general. So any more questions about the algorithm before I go on? I'm going to run out. Okay, so yeah, so that was a general theory. Now we take the inventory problem, and it's just going to be a special case. And I won't go through all the details, but the only thing to remember is, let's see. So we're going back to the inventory problem. Y is going to be inventory. A is going to be the amount of stock that we're ordering in a given period. Beta is going to be our time-varying discount factor. And you can see that it depends on Z. So it's depending on this purely exogenous state process. Or the state process has an endogenous part and an exogenous part. And I'm just assuming that the discount factor is only depending on the exogenous part. That's just a special case of what we looked at before. I'm going to skip the details about when it's going to converge and so on, but they're pretty straightforward to check. And let's jump into the code. All right, so I'll show you the Bellman equation just one more time. Yeah, so if you can just kind of like commit that to memory as best you can, or keep the slides there and then we'll look at the code. And that's what we're going to be implementing. So any questions about that?
Is there an interpretation for the spectral radius mean less than 1? So if beta less than 1, we know that you care less about the future.
Yeah, that's right. So beta less than 1, yeah, so that we want the spectral radius. In this particular model, what we want is the spectral radius of this guy to be less than 1. Now, if beta was equal to a constant, then the spectral radius of this guy would be exactly equal to beta. So yeah, this a positive discount rate. Now, allowing beta to be time varying and the spectral radius to be less than 1 means it's some kind of approximation of that. So like, on average, we have a positive level of discounting, so beta is going to be less than 1 most of the time. But it'll depend on the particular nature of the stochastic process and what's going to blow that up. Obviously, if you get large beta values, that's going to blow it up. Also, if they're very persistent, that tends to blow it up as well.
Is there like a real world example of a situation where the essentially the discounting part kind of is different with respect to different policies?
Yeah, good question. So I think the question is, when we looked at the general model, we allowed the discount factor to depend on the action. Here we're not doing that. Are there models where the discount factor depends on the action? So I think there's not that many people that are using state-dependent discounting in their models, but if you go back to the growth models of Uzawa, so in those models, the discount rate depends on consumption, which is one of your actions.
Essentially what you're saying is like you have to make sure the spectral radius, like of the largest L is still less than 1, but like the largest L, it seems like it's the largest L across policies.
It is.
Which means that therefore there has to be like some model where L is actually varying across policies.
Yeah, that's right. Yeah, so I'm just allowing for that extra generality following chapter 6 of the book. And there are models where discounting depends on actions. That would be one example. Any other questions, comments? I'm totally running out of time, so we're going to shift over to the code. To do that, F11. All right, so let's have a look at some code. One way to find the code, it is uploaded to the DSE conference GitHub organization. Another way to find it is to go to quantecon.org, and we'll go to the GitHub repo. Sorry, the GitHub organization, which has a collection of repositories. If you click on repositories, you'll find one that's called DSE2023. And it's up the top because I recently pushed to it. And if I click on that, it's got a bunch of executed notebooks. And it's got some Python and Julia code in it. When I write code, I never write code in Jupyter Notebooks because they're just a pain to work with. So I always write raw source code. In my case, using NeoVim as an editor, and then I've got some scripts in there that transform this into the built notebooks. So what we'll do is look at the built notebooks, but if you prefer just looking at code written in a text editor, you can also look at the underlying Py and JL files. As for the built notebooks, so I've got them. So these are all the built notebooks. And I've got them in Julia, and then 4 different flavors of Python. Since time is short, I think I'm just going to skip over the Julia one, but it's there if you're interested. I'm not a super competent Julia programmer, but I have been taught by good people, so I'm passably good. So it's not ruthlessly optimized or anything like that, and a good Julia programmer could probably squeeze a bit more speed out of it, and if they do, please tell me about it. Send in a pull request or come up and say hi and tell me how you did it, because I'd like to hear. Setting that aside, let's look at a couple of different ways that we could solve this. One is using Number, which has been around for a long time, and it's a library that allows us to just-in-time compile Python code. People who've used Number here? Just about everyone, so that's great. Okay, so the code, there's a bunch of boilerplate at the start under model and primitives where we're setting up the model. And I'm actually just going to skip over that, but feel free to bring me back to that if you have questions about it. I've got 3 different dynamic programming algorithms. Let's try and get back. One of them is value function duration. So value function iteration, pretty straightforward. I pass in T, which is the Bellman operator, get greedy, which computes greedy policies. And the heart of the algorithm is just this line here. Nothing very exciting there, so I'll keep going. The next one is optimistic policy iteration. I'm going to pass in a policy operator, and I'm going to pass in a get greedy function. And then you can see the heart of the algorithm is just here. And I'm doing exactly what we described. So take a V, get the greedy policy, iterate M times with the associated policy operator, get the greedy policy. And the last one is Howard policy iteration. And you can see here that I'm doing exactly what I promised I would do. So we've got a policy, we get the lifetime value of the policy. Once we've got that, we get the associated greedy policy, lifetime value, greedy policy. Yeah.
Are you getting the lifetime value by iterating?
Yeah, good question. Okay, so I'm calling this function get value. What does get value look like? Right, so now we get into the code itself. Yeah, this is just plotting code, which we can skip. So get value in this particular case, let me answer your question directly. So this is the get value function. And here I'm doing it by inversion.
Oh, and you could also iterate it until convergence, which is why you said that when m is infinity, it's the same.
Yeah, that's right. Yeah, that's essentially optimistic policy iteration with large M. Yeah, but here I'm just using np.linearity.solve to invert the identity minus L sub C. So usually when I solve problems, I use number first for pretty much everything, and that's because I like writing things in loops, and I really hate writing vectorized code. People are so split on this. Like, who likes loops? And who likes vectorized code? Yeah, it's like 50-50, something like that. So I think in terms of loops. I always write things in loops first, and then I somehow put together the vectorized code and pray that it works, and test it against the code with loops, and then off we go. So this is number. I've written everything in loops. Like I said, that's my starting point. So usually what I do is I write, this guy here is the right-hand side of the Bellman equation. So if you think back to the Bellman equation, for this particular problem, it looks exactly like this. That looks super weird, but that's a beta. It's just rendering in a really strange way. So that's the right-hand side of this particular Bellman equation. So I usually write a function which just implements that. And then I maximize with respect to A, or I put in a particular policy, which gives me the policy operator. And I'm using ng to just-in-time compile this. All right, so we've got these different functions. We don't quite have time to go through all the details of the different functions. Here's a solution. The solution in this particular case was computed by, let's see, optimistic policy iteration, but it's actually the exact optimal policy. I know that because it's the same thing that was returned by Howard policy iteration. So what you're looking at here is inventory over time in a simulation. As promised, inventory goes down, down, down as demand draws down inventory, and then there's a jump up. This is because of the fixed cost of ordering, so we wait, and then make a large order and drop down. The other thing that we see is going on is that there's changes in the overall size of inventories depending on the interest rate. When interest rates are low, not surprisingly, we're happy to have high inventories. When they're higher, we prefer to have low inventories. So this stochastic discounting is having a pretty big impact, in this case, on the policies and optimal actions. And I'm going to run out of time, so let me just quickly then jump to the timings. So this is the timing for number. What you're looking at here, this is M. So M is the index in optimistic policy iteration. This is the time that's taken. This one's Howard. The blue one is value function iteration. And optimistic policy iteration is kind of looking like we promised it would. So if M is equal to 1, it's the same thing as VFI. If M equals infinity, it's going to be essentially the same thing as Howard policy iteration. But actually, like computationally, like we're never going to take M out to infinity and like if we do take it super large, in fact, that's going to be really expensive. So normally what we see with optimistic policy iteration is it's going to dip down and go back up again. And in most models that I solve, I find that there are values of M where OPI is beating Howard, but not in this particular case.
Would you, sorry, quick question, would you take M as being smaller, let's say at the beginning of the iterations, the main iterative water loop, and then towards, let's say, when you get closer to convergence, you get.
Yeah, that's a really interesting question. I haven't played around with it.
Okay, so you have to fix that.
Yeah. And I don't know if there's any theory that speaks to that.
You get a cruder approximation of that.
Yes. Yeah, makes a lot of sense.
Why do you call it optimistic?
Good question. So that's not my name. That's like just reading books like Dimitri Bertsikis's books.
Is there like what's optimistic about this?
What's optimistic about it? I guess you stop before you get to the full lifetime value and you hope it's pretty close. It's the best I can do. All right, I'm just about out of time. So let me just really quickly look at the JAX code. We've had a good amount of questions right through, so I'll talk up to, I can go until 20 past 5 minutes. Okay, yeah, so let's just quickly look at the JAX code. What do I do now? This 11. The JAX code, I've written 2 different flavors, and I'll show you, since I'm running into limited time, I'm going to show you the JAX linear operator method, which I promised to show to a couple of people, so I better do it. Okay, so we're now going to use JAX. I like JAX because JAX is like low-hanging fruit. It's really easy to take something and put it on the GPU. And you know, when I hand-coded things to go on the GPU using number CUDA, I would think that I'm really smart and I did a really good job. And then I'd put it in Google JAX and realized that actually I was woefully inefficient and Google JAX was massively faster. So these days I just tend, if I'm going to put something on the GPU, I tend to use Google JAX. I like JAX for that reason, and also because the code is the same whether I'm going to write for the GPU or the CPU. JAX detects the CPU, it's going to put the it's going to write machine code that's optimized for the GPU and put it on the GPU. If it doesn't, it's going to run it on the CPU. So that makes it super easy for me to test with small models. And then when I've got something I want to do seriously, shift it over to the GPU without actually having to change the code. All right. So the dynamic programming algorithms are exactly the same. The plot code is the same. Let's skip it. Things start to get different when we write the right-hand side of the Bellman equation. So you saw that in number, and now we're going to do it in JAX, and we have to do everything vectorized. So like I said, I'll do everything with loops first, and then somehow write all this out and just pray that the 2 things agree. Once they're happy and keep going. So this is the whole thing vectorized. There's no for loops. JAX is relying on that because it wants vectorized code in order to compile things efficiently. And I have to admit that once you've done that, things like the Bellman operator and the get greedy routines are going to be pretty slick. Simple to write. Okay, the one interesting feature about this thing that I'll say in closing. So you remember that to compute lifetime values for Howard policy iteration, I need this L sub sigma matrix. So in the JAX code that's in the other lecture on JAX, I instantiate the matrix. That's one way to do it. So I've got, it's like identity minus L sub sigma that I'm going to invert. So I build these big matrices. Now, if we do this for large problems, that's going to be problematic because this is going to be, if the size of the state space is n, it's going to be n by n. if n's even like 100,000, this is going to kill you. So what this does instead, I'm writing it like an operator. So all I'm saying is think of a matrix as a linear operator. It's just the right way to think about a matrix. It takes a vector in and it spits a vector out through a linear operation. And I'm just going to describe how that happens. So then I'm going to pass it in something that's of size n, and I'm going to get back something of size n. I'm never building an n by n matrix. So I define this as a function, and then when I call the solver on this guy, so here I'm calling the solver, this a sub sigma is exactly a sub sigma is exactly L sub sigma. So this Jack solver here that I'm using works on linear operators. It doesn't require me to instantiate the matrix. So that's, I guess that's the way that you'd work with what you might think of as sparse matrices. In this case, we're just working directly with the linear operator. That tends to be a lot more memory efficient. If we move into big problems, it becomes the only feasible method, but it's also tending to be faster than instantiating matrices anyway. I think I better leave it there. Thanks for listening.